Good to go? Alright. Alright. Hi, everyone. Yeah, let's get started on string gauges. So, first off, as a quick preface, string gauges are a really useful tool for us on the team. We started developing with them, I want to say 2 summers ago. And they basically allow us to get forces and torques and essential information through our members, like all the car itself. So camber links and tie rods and axles, and we just get to get all those little pieces of data that you use in your physics problems and whatnot, which allows us to solve for different things on the car. So, because most people in here are probably non-mech, I don't know what exposure you've had to this kind of stuff, but there's 3 types of loads that can be applied to a member. You have your axial load, where you have a force being applied in sort of in the same direction as the direction that it's fixed on, and that causes the member to be elongated. It just gets a little longer. In bending, it's kind of what you think. You have the member fixed along this axis or along this sort of vertical. You apply load, and then the member will tend to deform. And then under torsion, same thing. You have your member fixed along this axis, and this usually happens more with cylinders than with rectangular members or rectangular 3D members, but they just twist. So those are your 3 kinds of loads that we see, and we see them all over the car, like in the axle and in the drive shaft we see torsion, and then in the tie rod and the camber link we see axial loads. So these are pretty much seen all over the car.
Where is bending?
Bending. Bending we see on the engine runners. So you have your big engine that's a mass, and it sits on here, and it's pinned on these 2 sides. The engine mass hangs down right in the middle, applies a load right in the middle, and this will tend to deform just like that. And we can get the sort of the force that goes through this member as well, which is that's bending. Singling out just axial loads. The way that a material deforms in a more static sense is when you apply forces in 2 directions. You have what's called tension, and then the other way you have compression. Tension causes the member to elongate by some certain amount, by some delta L amount from the base L value, or the base L length. And in compression it's the opposite. This also adds, I think it's by like the Poisson's ratio or by the Poisson's factor, the member also just like gets thicker, gets thinner, depending on which direction the load is going, since you have to keep your volumes the same. Oh, what's physics? You have to keep your volumes the same, so adding a load adding some sort of load, just deforms the member. And this is described through a value called strain, and that's what strain gauges mainly are used for, is they measure. These little orange sections on there are strain gauges themselves, and that's sort of how they're applied on a member. And they are applied on something, and they deform in the exact same way that that member will deform. And the way that that is measured is through strain, which is a relationship between the amount that something extended or compressed by over its just normal length, and it is expressed as a percentage. So this is what a strain gauge itself looks like.
So cute, it's really nice.
Yeah, it's.
Good drawing. I love the diagrams. Yeah.
Yeah, so it's a little piece of plastic that has a lot of really thin conductive pieces on it. It's called the measuring grid itself. And the carrier material in the back is usually plastic, and that plastic is what you actually lay down on the surface. The plastic is chosen so that it can deform pretty much as the material deforms below it, providing no resistance, and it doesn't want to compress when the member is elongating. So if you have a member that's getting bigger and it'll want to make the carrier material bigger, it won't resist that as much. It'll just let the measuring grid deform as it feels like deforming. This is just one type of strain gauge. This is just one type of strain gauge. There is a bunch more, which I'll get into a little later. But yeah, like I was saying, both the carrier material and the measuring grid, the property, like the material properties of those are chosen so that really you only get stretch, or you really only get deformation in the axial direction of the strain gauge itself, sort of in here versus the transverse direction. And that's really because we want to be measuring strain, or we want to be measuring the deformation of this resistive pad right in the middle, only in the axial direction, since that'll provide the most amount of change. Compared to the transverse direction, you're not really going to see as much change in, for example, the thickness of these little wires, because that's sort of the basis of how strain gauges work.
Wait, sorry. Can you go through that just a little bit again? So
Yeah.
that it's just saying that on the car we mostly do axial, is what you're saying?
We do axial bending and torsion on the car. Like
Okay.
those are different kinds of loading that we see in the members. But in terms of how strain gauges themselves work, they
Okay.
mostly work under axial axial stretching, or axial loads, and that's yeah. So you position your strain gauges on the different members so that you really only see axial loads on the strain gauge.
Right, I see, and we're not picking up a different force instead.
Exactly. Yeah. Yeah, so the working principle of strain gauges is through the resistance equation. This is an equation for actually determining the resistance of a piece of metal or something that's conductive, or a conductive material, more like.
Oh wait, we should tell people in the chat. If you guys have a question, just shout it out.
Or drop in the chat.
Or drop in the chat. Sorry.
Yeah. Yeah, the resistance equation itself is described by a material property called resistivity, and then the cross-sectional area, and the length of sort of the wire, if you want to think about it.
Yeah.
As you pull a material, or as you pull a wire, like imagine yourself, you have it on two ends and you're stretching it out, the cross-sectional area of the material is going to decrease. So I'm sort of going from here to there. The length will increase, right, because you're stretching it out. And then fundamentally for the resistivity part, the density of, I think it's the atoms that are inside, like that are actually making up the material, gets stretched apart, because you're keeping the same volume, right, but it's just the spread of those atoms, I guess, within the material that gets stretched out over a longer length, and that allows electrons flowing through to be able to travel a little bit less impeded. So when you stretch out your strain gauge, for example, you might tend to see a decrease in resistance, because you're going to see that current will be able to travel through all of these little paths, I guess, a lot easier than when it's just like static.
V stays the same. P equals IR. Also.
It's all going back.
Yep. Typically for strain gauges, you'll see a resistance of 120 or 350, like just as a base value. That doesn't mean, if you like get two strain gauges, one of them is 120 and one of them is 350, like base ohms or base resistance, that doesn't mean that they're going to behave differently or the same. That differently or the same factor depends on the gauge factor of the strain gauge, which is like the third, or like one of the main other properties that you're going to see when you're buying strain gauges. They're going to list the typical resistance, they will list probably the gauge length, and then the gauge factor. Those are the three main things. The gauge factor relates the change in resistance. So effectively, remember that the strain equation is this. This is basically like resistive strain. It's how much the strain is changing per a unit of, or sorry, how much the resistance is changing per unit of resistance, which is also a percentage. So you have essentially your like percent change of resistance and your percent change of the actual material length, and that determines your gauge factor. There's like a whole way of describing it where you look at like the stress strain curves, and you look at, oh, what is this slope? Like this is R and this is epsilon. And you look at like this slope, instantaneous slope right here, and I don't know. It doesn't matter. It's just how that gauge factor is determined. It's the slope of that. But when you fundamentally want to look for strain using the strain gauges, like you put a strain gauge on, and I want to know the strain at this very location, you know, I want to know the strain right here. What percentage of strain am I seeing right there? You know your gauge factor, you know your base resistance, and then you measure your change in resistance, and fundamentally then you can get your strain. That is like the way that most people use strain gauges. Not necessarily how we use it all of the time. We mostly calibrate the strain gauges to go directly from resistance through Wheatstone bridge, so through an amplifier, directly to force or to torque. So we go from voltage to force or voltage to torque. But this is how you're meant to use them. Yeah. Now the way that you measure sort of a change in resistance is Wheatstone bridges, because you can put your multimeter up to a resistor and you can get your resistance, and oh, that's great. What do you do with that? I don't know. That's not an analog value that you can read with an Arduino or with an ADC or anything. It's pretty useless. So we use Wheatstone bridges, and Wheatstone bridges are a way to translate a change in resistance or just any difference in resistance into a difference of voltage. And the underlying principle is you have 4 resistors. I'm sure you guys know this.
Oh.
I don't want to remember this.
I'm sure you're very familiar with it.
Second year core.
Yeah.
This was some-
Week.
This is like 2CI, 2EI.
One-
Yeah.
The mechanical students did this.
The last year.
We did it.
Yeah.
You guys have an electrical course.
No,
Yeah.
this
Oh,
was
yeah.
a mechanical
Oh.
course for us
Oh.
as Tron.
Oh.
This was in our mechanical measurements
Damn.
course.
Yeah. Well, then as a refresher for most people, and
No circuits.
new for some people, this is a Wheatstone bridge. You have 4 resistors in this arrangement. You have power being provided on this side, and you have 4 nodes. And through a concept of voltage dividers, you're able to get the voltage out through each of these legs at C and at point D. That's sort of what this is. So you know your VA. You know VB is whatever your V minus is. So for most cases, it's 0 volts. So let's say, I don't know, there's just some X voltage. And let's say it's 5 volts. And we want to know what voltage at C is. You can relate it through this equation, where you know your resistor values, you know your input volt, you know your output volt, or you know your sort of your volt low and your volt high, and you want to know your VC. You relate it through here. And the bridge is balanced when VC and VD are the same. When VC minus VD is 0, you have a balanced bridge, because that means that the voltage going through both legs is the exact same. And that means that your voltage at A minus your voltage at B is also 0. Because that means, yeah, you're just using everything you got. You can use some Kirchhoff's law to derive this if you want, or just take my word for it. To balance the 2 sides of the bridge, just using pure resistance, you can use this equation. Yeah, and that reiterates what I was saying. The more fundamental way to solve this is saying that the current is 0 through this sort of in-between bridge, but you can say that the voltage at C and D is also 0. And then for strain gauges, it gets a little different. Where did I put it? Oh, it's okay. Yeah, for strain gauges, one of the more basic ways that actually we started out with as well, for measuring the voltage, or just like measuring the change in strain, is by replacing R2. You replace R2 with a strain gauge, and that becomes your variable resistor. And now anytime, or as an example, if you set R1, R3, and R4 all to equal like 350 ohm, your R2 strain gauge has a base value of 350 ohm. Great. Any time that R2 is more than 350 ohm or less than 350 ohm, your bridge is going to be unbalanced. And that unbalance is going to come through in your VC minus VD not being the same. This will not be true. And from there, what we would do is we would take that imbalance, we take the actual value of VC minus VD, or we take the value of VC minus VD, and we would calibrate that against whatever force is being inputted on that member in the real world. So when you say you're tying a tie rod by 2 ends, and you're stretching it out, your R2, your strain gauge on the member is going to see some sort of deformation, right? You're going to get some strain value there. And whatever strain value that you see there will be outputting a VC minus VD value because it is not balancing the bridge. And then you do that a bunch of times, and that's how we have calibrated our strain gauges in the past, is by doing that. Replacing one strain gauge in the Wheatstone bridge, or replacing one resistor in the Wheatstone bridge, is called a quarter bridge. There's also half bridge and full bridge configurations. For strain gauges, you replace, for a half bridge, you replace R1 and R2. So those both become strain gauges. For a full bridge, you replace R3, R4, and R1 and R2. And there are a couple advantages to that. Yeah, quarter bridge, yeah, I said R4, but yeah. R4 is one, the rest are all the same. For a quarter bridge, it's really easy to get into. You can just put one strain gauge on. The application method for this one is really easy. And then you just find three other resistors that are more or less the exact same, 350 or 120 or whatever your case is. And then you do your Wheatstone bridge construction, you amplify that value of VC minus VD, and it's relatively easy. But one of the things that changes resistivity, or that changes resistance of a resistor, is temperature. So your material properties fundamentally change for your strain gauges, and then also the material that you're laying your strain gauge on, whether it's steel or aluminum, will also change through temperature. It will expand or it will contract. So by adding more strain gauges, like replacing more strain gauges in your Wheatstone bridge, you're able to compensate for that temperature change. For example, if both R1 and R2 go up by the same amount, just because you've gone from a room that's 0 degrees to a room that's 20 degrees, and R3 and R4 stay the same, your bridge will still be balanced, because your VC is going to be the same as your VD, no matter what, even because your resistance values on both sides of that voltage divider, like this voltage and this voltage, will more or less stay the same. So that's how you compensate for temperature. And then same thing, but for a full bridge. Another important thing that we want to do, which is why we mostly make full bridges these days, is to compensate for different kinds of loading. So say you have your beam, it's pinned on two sides, and you only want to measure forces that are going axially inwards. Say this is like the tire on the car, or just this beam. You only want to see the axial loads, but all of a sudden you get like rammed in from the front. You're driving your car and you hit a tree or something, and all of a sudden you get a big old bending load. Well, I didn't want to see a bending load. I don't want to see how much force that caused. I wasn't expecting, I was expecting the tie rod to fail in the axial loading. I wasn't expecting to see it fail in bending. And I only want to measure the forces in the axial direction. So I don't care about these forces. I only want to see the axial ones. You compensate for that by making a full bridge. And by doing that, the way that it looks, and this kind of helped me to visualize it. So you have strain gauges on all four sides. I'll just do a little like dotted line back there or something, I don't know. When you experience that load, compressive load going inwards, all four strain gauges are going to see that same compressive load, right? Because they're all being deformed inwards by that same amount. But when that bending comes in, the strain gauge at the top, let's say it looks like this. Strain gauges on the side, if you remember from up here, we talked about how strain gauges are designed to really only see forces in the axial direction that they're placed on and not the transverse direction. These strain gauges on the top, kind of just like this, they are going to get stretched out. And these ones on the side are not going to get stretched out as much because they are going to get stretched out in this direction. So you're only going to see, for the most part, a change in resistance for the top and for the bottom ones, right, compared to the ones on the side. And by building a bridge with 4 strain gauges in this orientation, you're going to be able to cancel for, or you're going to be able to compensate for loads that you're not expecting. So So this is a really nice table that I found. It talks about all the different bridge configurations for how to form your circuit, where you want to put your strain gauges for all the different kinds of stress or load that you're expecting. So just like for this first one, for example, this is like one of the more basic ones that even we were talking about for the most part. You're only seeing uniaxial loads, right? You're only going to expect to see that. You're not even going to expect to see bending or anything else. So all you need to do is you need to replace one strain gauge, or you need to replace one resistor with a strain gauge in your Redstone bridge. And this, see, this has less ambient temperature, or less ambient temperature changes and no temperature compensation. And they're only expecting to see axial loading. You can compensate for temperature also by using a strain gauge that has 3 wires. Like 1, 2, just looks like this. Or by just using a strain gauge that has 2 wires, and then you sort of like loop it back here in the triangle, like put it here and here, and then you also put it up here or something. There's a way to do that. It's also in this chart, but that'll also help compensate for temperature. I personally have never done it because we've always just had an abundance of strain gauges, and they're really cheap. You can get 50 of these little bad boys for like $20 or 100 for $20. It's really not that bad. They're pretty much disposable. And you're going to find when you're applying strain gauges anyways that you're going to ruin about half of them. Just in the application process, it's not perfect. Even like me and Schmitty, who have been applying a lot, I've been applying for like the last 2 years, and he put on like 16 in the last couple weeks for his wheel force transducer. Even he's found that it's like a 50% chance if you actually get it right or you don't. Even if you line everything up and you get it right, the chance that it'll actually stay adhered and it'll actually work the way you expect is not great. But I'll get more into application in a little bit. Yeah, I don't tend to use these types of these types of configurations. More so these, so these have temperature compensation. You have your strain gauges on 2 sides of the bridge. These are half bridges. These ones, also it matters like the configuration, like we were saying, which direction the strain gauge is being loaded. This one is being loaded transversely, this one is being loaded axially. So that'll help this strain gauge to essentially act as a dummy, and this one to act as the actual active strain gauge. So that's why they say 2 active, or 3 active, 2 active, 2 dummy, That's what they mean when they say that, if you're ever referencing this table again. What else we got? Other interesting ones. Yeah, some of these are interesting. You can play with it. This is a cool one. Temperature compensation, and this is only meant for bending, so you're canceling out compressive and tensile strain. This is pretty cool. Same with these. Just canceling out temperature by having dummy strain, or dummy gauges, but you don't really cancel out bending, I guess it is. Yeah. There's also some literature about canceling out the lead wires themselves. They have like thermal effects. The resistance of the wires themselves that you connect to the strain gauges might have some weird effects with the resistance that they carry. So depending on your configuration, you can also play with that. Here's some of the torsional ones. These ones are pretty cool because under a torsional load, right, you have your member, if it's fixed on this side, you have your member undergoing a moment. You're twisting it. The principal direction that your strain gauges are going to be deforming in is going to be along the 45 degrees. And because of that, you place your strain gauges in a 45 degree to the vertical, or the 45 degree to this point. Let's fix on this side. Yep. So that's where these configurations come in. These are gauges these are like gauge types that have built-in strain gauges already in those perfect angles for you. Those are really nice. I started experimenting with those this year as well for the axle on 23. Actually, it has this type. They look like big little squares. I got 2 of them. I have gauges,
Yeah.
kind of just like this. Yeah, and they have 3 pads. This one goes here, this one goes here, this one goes here, and this one goes here. And it kind of makes bridge building already easy for you because they already set up half the compensation,
Right.
so you don't need to wire as much. Yeah, I saw this last night. I was like, that's so wacky. I don't know why you'd ever do that.
Wow.
Yeah, what?
Is
No,
that-
no temperature.
Yeah, there's no temperature compensation.
Just the average.
Yeah. And it's meant for mean strain measurement. So strange. Yeah, so this is, I keep talking about tie rods, but here's a bit more of an example of like 2 cases where you're going to see axial loading. So it's kind of hard to see with all the colors from all the different colored filament, but you have your forces. Say your driver has the steering column going right here, and they're inputting a right turning force, which is going to put this force right here onto the tie rod, and you're going to see that force going through in this direction. Imagine your wheel is fixed, because instantaneously, when the driver puts any sort of load into the steering wheel, the wheel itself on the ground is going to try and resist that load by inertia, by friction, just by it being there, as long as you're actually on the ground. So then you're going to see a force in the tie rod, which will be equivalent to the force that the driver is putting in by inputting a torque onto the steering wheel. So that's one way you can get like steering effort almost. And then the opposite effect, say you get rammed in the side by someone, like you have your wheel.
You're getting T-boned.
Yeah, you get T-boned. If this is like a top-down view, for
You're
example.
racing against Kai.
He's feeling aggressive that day.
Honestly, more like Schmitty.
Oh my
Schmitty
god.
and Kai, go
Yeah.
parts.
Battle it out.
Say this is your wheel. This is like a top-down view. You have your wheel. You're getting, it can pivot about this axis. You're getting hit like right on the front of your wheel. That'll force your wheel to go in like this. You're going to see that force because the tie rod doesn't pivot about this point. It pivots about like a point out here. You're going to see your tie rod. You're going to see the amount of force that's put in that direction. So this is your force going in, and you're going to see that force through the tie rod. And then you're going to see the force through your steering rack, which is the principal thing that we're doing for design press for controls, is trying to justify the steering rack, and we're going to try and get tie rod data, but probably end up taking tie rod data from last year for it, which would be pretty cool. Using the data, not faking it. That's just fun. Yeah, so I sort of talked about this at the beginning, but some other applications, some of these I've actually tried to implement, some of them I've thought about. Tie rod and camera link we've done on 23. Camera link we did on 21. That was like sort of the very first thing that we did. Steering column, axles and drive shaft are a little more difficult. Axles and drive shaft are difficult because they're constantly spinning, right? So just this year I started developing a wireless strain gauge PCB that'll do all that, and it'll be a PCB that sits on the axle. I'll get to that later. The steering column is a little easier to implement because it stays in place, but what happens when you want to take out the steering column? We got wires there. I don't know. Maybe they get snipped. Maybe they got snipped without me being there. I don't know. Maybe we got a nice apology from Bart when he did that. And then engine runners, I was talking about it with Anshul and Brennan a little while ago. It's pretty cool to do engine runner strain gauges to actually see and validate, sort of complete that design cycle for the engine runners, to be able to design them to be as small as possible and still be able to take all the vibrational load from the engine, and then actually be able to see how we can minimize the material selection for that, because right now they're just like insanely overbuilt. That'd be pretty cool. This year, I want to do this, maybe this, and we'll see about that if we get to it. But for sure, I think these are 100% achievable. For steering column, it's just a matter of figuring out how to make it removable, right? Or how to make it be able to slip in and out when they want to take the steering column out. And then axles, it's about figuring out, axles and drive shaft are about figuring out the wireless stuff. And then, yeah.
You could 3D print something that sits on the steering column.
Yeah.
Screws it in like a collar.
Yeah. Gotta think about it.
Because that's what you want to do with steering position.
Ah, yeah, actually, I was gonna ask you about that.
Yeah.
I think.
So we can talk about that. Maybe, yeah.
I talked about applying a little bit, but over the last year we've developed a pretty nice process for how to actually apply strain gauges, and this still has like a 50% success rate. So if you find any research, especially if you're reading that textbook that I sent a little while back, you don't need to read the whole thing. It's really long and really in depth, and this guy in the foreword, he's like, oh, I've been working with strain gauges for 30 years, here's what I've learned. I hope I never get there, but there's some pretty good information in there, really good reference material. If you ever want to just get a bit more into it and not just take what I'm saying as gospel, if you want to see it from someone else who can describe it a bit better, that's the guy to go to. But in terms of actually applying strain gauge, you prep the surface, so removing the dirt. It's a couple different processes of making sure that surface is nice and flat and clean. So you remove your dirt, you remove your dust, you scour it so it's rough, and then you sand it down so it's nice and smooth. And then to actually get the CA glue to adhere, you want it to be rough again. So you do scour, sand, isopropyl, get rid of all the dust, scour again, and then isopropyl or acetone, they both work. And then you line up your strain gauge. So for axial stuff, you want your strain gauges to be like perfectly in line with the direction that you're expecting to see the force, and that includes the top, bottom, and back. If you're running any type of compensation and you need dummy strain gauges, if you have axial, you'll want to set them up perpendicular. So you're going to want to make sure these are like 90 to each other, and that's pretty much it. And make sure, the way I think about this is you set up this one first because you want to see your axial and you want your principal strain gauge to be able to be in like the perfect position, and you kind of just place this one more or less eyeball it to be perpendicular because it's going to be dummy and you're not really going to see much in it anyways. What's also mentioned in that video that Ariel posted is these dummy strain gauges that are just used for temperature compensation, not for load compensation, just for temperature, can also be placed on an adjacent member that is not seeing any of the same load at all, but is also being affected by the same temperature. On the BAW, that's not really going to happen anywhere because the chassis is not infinitely rigid. It is a spring. Unless there's like, I don't know, there's like a 3D printer, there's some other material that's not directly connected to the suspension, then you can maybe place it on that, but for the most part, this has been pretty reliable for us. So, yeah, so you gotta line up your strain gauge. You can use a jig or to get this perfectly in line, like to get this first one in line, I use like a scribe line. You just like scribe into the aluminum or into the steel, and you sort of use that to line yourself up. Hold it partially down with tape, so masking tape on one side so that you can remove the masking tape and the whole strain gauge will come up, but masking tape still allows you to keep it in position, which allows you to put some CA glue down underneath your strain gauge. Hold it down with your finger or something over the tape for 45 seconds, a minute, minute and a half. Wait for the CA glue to set, and then remove and let it cure for another minute or two so that it's nice and solid and you can keep going. One of the things with putting strain gauges close to each other like this is you're going to get like CA glue here unless you get really good at it, or maybe you're even going to get it like here, right? And then you got to clean that surface up before you apply the dummy one. So that's why sometimes it's, even though you want to get all your strain gauges put on fast, sometimes it's good to get all your principal ones on and then come back the next day, clean off the surface properly, and take your time and put the dummy ones on there too. And then you got to wire it up. In the beginning, we made this Wheatstone bridge set up off of the tube itself. And this made the most logical sense is, oh, let's just take all the resistors and take them off the tube, which is going to end up being like 8 wires. It's 2 for each, and then you deal with it afterwards. You deal with it on the board. And this also makes the most sense if you're doing anything less than a full bridge. So if you're doing quarter bridge or a half bridge, you're only dealing with, for quarter bridge, you're only dealing with 2 wires coming off of the tube, and for half bridge, you're dealing with 4, which honestly isn't that bad. And if you're doing either of those, then you're gonna already need to use dummy resistors anyways somewhere. So you might as well only take off 2 or 4 wires. But then for a full bridge, it really doesn't make sense to take off 2, 4, 6, 8 wires off the tube. So what we do is we
Sorry, how do you get off the tube?
grab your tube, you have your strain gauges, and you have your wires that need to go to like the DAC box or
Okay.
something. So instead, what we do is we actually build the bridge configuration on the tube itself, or on the member itself. And what we send back as wires are A, B, C, and D. And we deal with those on the PCB, which I'll get back to the PC in a bit. But that just helps to simplify the wires going back. It helps to unify. Like, we can use a wire that has 4 individual strands in it that are like red, black, green, and white, and we just know what they all mean instantly. It's been pretty useful ever since we started doing that. And that's what I mean by, that's what I mean by this part. Just recently, Schwede found relief pads. So they're, let's see if I can find a picture. They're basically, you have your strain gauges on, your strain gauges on a tube. So this is one way to do it. You apply your strain gauges, and then you just solder wires directly to all the contact pads. And I think these guys also made the bridge on the thing, so they're just sending back 4 wires. Send back those 4 wires of the Wheatstone bridge and you deal with it later. But this, you need to actually CA glue down all your wires, and you need to make sure that they're in the final position. And one of the main issues with us is when these strain gauges are forward facing on parts of the car that are exposed to the elements, these solder joints will probably not hold up as well as you're hoping. So we either put conformal coating over top of this whole resistive pad, or we put electrical tape or something like that. On the 23 axle, you'll see an IGUS bushing plastic bag that's wrapped around to just keep everything inside and to make sure that it doesn't get like physically dusty, right? So that's a pretty big issue. Let's see if I can find a good picture. This guy went overboard.
Holy shit.
I would not do this. I don't have the patience for this. But you can see over here, this is what I mean by strain relief. So your strain gauges will come with, this is also the strain gauge I like. This is like the torsional one. You can see it's like 245 degrees. I think they're doing torque on this member. But the strain gauges will have wires pre-attached to them, or you're going to put on very, very thin wires onto the strain gauge. You usually don't have to solder those. You solder them to a plastic pad. It's a rigid plastic pad that has copper directly on it, and it's meant for you to solder one end of the strain gauge, like the wire coming right off the strain gauge to that pad, and then your actual wire that you want to use on the other side. You CA glue these down. Maybe this is a good picture if it wasn't such bad quality. Oh, here. That's a good picture. Yeah, this is actually exactly what it looks like most of the time, except it's not more than one connector. It's just one piece of copper, just like this. But you CA glue this whole row down, and then you solder your strain gauge wires to it on one side, and then the Wheatstone bridge wires on the other side. And this also lets you, like we saw in that first picture, create your bridge just using wires on this pad. In fact, I was doing that the other day. Yeah. I actually did something just like this guy, with this green wire bridge in between 2 pads. Makes it super easy. So that's what these relief pads are. And then usually, up until this year, we haven't added connectors to the tubes themselves. Because you'd be like, oh, why do the tubes have connectors? That's a weird thing to like a mech kid. We've just like had 4-foot wires coming right off the tube going right to the back of the tie box. Which whenever the tubes need to come off for whatever reason, like the tie rod needs to come off because we need to do something with it, or the camber loop needs to come off for whatever reason, it needs to be worked on, we have to snip those wires, we have to snip the strain gauges. and it's one thing to resolder them, but CA glue is temperamental to really, really high heat, and these wires, because they're so thin, they transmit heat or they transmit temperature really, really fast or really, really easily to the CA glue joints, and it doesn't have a fun time. Strain gauges, don't ask me how I know, also burn off really easily when you put a soldering iron to them. So you don't want to heat soak those. But yeah, this is the exact configuration. Usually I use, they're not really plus and minus, they're just two analog outs. They act as two analog outs, and this is what we send back to the PCB that has a Wheatstone bridge on it, which brings me to the PCB. So this is the current revision that we're working with, and this is the revision that will be used for the tie rod and the camber links and maybe the steering column. This board is kind of split into two, because you have like, out one and out two. This can handle two separate Wheatstone bridges. And the way that it works is you send in VCC, so 3 volts here. You send in your V minus, your ground, and then this is an ADC or an analog output that you send to a TNC or send to an Arduino to their ADC channel to convert an analog signal that's in millivolts, really, really usually low. You convert that from analog to digital, and then we use those values in the data viewer, wherever we want to use those. This is where you're doing your voltage. This is where you're doing your voltage to force, your voltage to torque transformation. You're doing it on the values that are coming out of this pin. Other things on here, we have we have one op amp and an instrumental amplifier. This is the op amp. This is the instrumental amplifier. You have an offset, which I'll explain what that does in a little bit, and a bunch of resistors and capacitors. This is the Wheatstone bridge, like I was talking about. These directly correlate to your Wheatstone bridge values. So your ground, your VCC, your 1A, and your 1B. And same with the other side. So that's a bit of an overview of that. And the actual circuit itself looks something like this. Again, sort of split down the middle. This is for one, this is for the other. So we can basically have a tie rod and a camber link working off of one PCB, is what all of this means. Now, the two main components, or the two main circuit elements that we're dealing with, is an instrumental amplifier, which is this one right here, and the op amp. I think it's easier to start with the op amp. Actually, no, let's start with this. So all this instrumental amplifier does is it amplifies the incoming out, like out one, or here, out one or out two. It amplifies that value into something that we can actually make use of. It amplifies it by this amount, or this gain. And the reason why you would want to change that is based on your material. For example, aluminum will tend to deform a lot easier than steel would. And for example, your axles might see a higher strain, like a torsional strain, than your tie rods at any given moment, or maybe even the other way around, depending on the configuration. So you're going to want to amplify the incoming analog values to a different amount to actually make sense of them, and to actually have them be granular enough to be of any use. That's what the instrumental amplifier does. It's sort of a translation of every component from here to here. Yeah. The main thing to note is this equation and how it relates to these two resistors, and the same thing for the other side. It relates to these two resistors for 1 and for 2. Yeah. So first thing to sort of troubleshoot when you plug in your strain gauge and you plug in your Wheatstone bridge and you hook it up to an oscilloscope, because that's how we read these things. You hook the Wheatstone bridge up to the oscilloscope, or you just hook this directly up to the oscilloscope, just this one right here. and you get your output, and you try and you pull your tie rod. This is like your base value. Do that different color. This is your base value right here. And you turn your tie rod, and all of a sudden it just goes right here. And this is 3 volts, and this is 0. And all you're getting is this little marginal change. The first thing that you do is you change your amplification through the instrumental amplifier. You change the ratio of R1 and R2. The second part of this that actually has the offset. This little it's a rotary pod. It doesn't render here, but it has like a little minus here, and you can twist that, and it's just a pot. It's a trimmer pot. Actually, one thing to know about that is most of the string gauge PCBs that we have right now, most of the amplifier PCBs, don't have this pot in, the trimmer pot, because the one that we got was really bad. So we just have 2 resistors going like here and like here. You can also play around with those, but that is for setting your virtual ground. So one thing that Ariel was thinking about when he was designing this is, are you going to see more torque or more force going in one direction than the other? And in my mind, the easiest way to think about this is through torque. So you have your engine, like your engine on one side, you have your axle, so you can see you have your engine on one side, you have your axle, and then you have your wheel. Right? The engine is going to supply some sort of moment, your wheel is going to try and resist that. Say you're starting from 0 and you're accelerating, and all of a sudden your axle is going to see some sort of torque going forward, right? It's going to be some amount from whatever the engine supplies, and then you get to your cruising speed. You're not really going to see any torque, any additional torque other than what's already being supplied in the system. And all of a sudden you hit on the brakes, and all of a sudden your engine is going to sort of be back driven by your wheels. Your wheels are going to want to stay still, and you're going to see a reverse torque in the opposite direction on your axle. It was a debate last year, and it kind of still is a debate, but which way, on the acceleration side or on the deceleration side, are you going to see more torque through that axle? I think it's on the deceleration side, like on the braking side, because it is more instantaneous, and the engine can only supply so much input torque, especially because it's going through the gearbox and through the CVT, so it's not really instantaneous. But that would be an argument for biasing your virtual ground to be more in the range, or more in like the direction of the range that you want to see something more granular. So the whole point of this amplifier board, just to take a step back, is to translate some input signal to be a signal between 0 and 3.3 volts, because that's what our laptop died.
Is it USB-C? I have.
Oh, true.
Yeah. I have HDMI. Is it plugged?
I mean,
It's this one.
Yeah.
Alright. Which one?
that's the source.
Okay.
Oh, do you want to plug it in? Do you want to plug it on this one? Because I already have it pulled up. Or.
Oh.
You'll bring your laptop over here.
Alright. I'm good either way. No signal.
Any questions so far? From anyone? My phone went off.
Hopefully, I don't want to just ask a question.
No
But
questions.
you're pretty clear about it.
Oh, damn.
Goodbye, Anna.
He has questions in someone else.
Goodbye, Anna. Yeah.
Alright, there we go. Alright. Yeah, so the whole point of this board is to amplify your strain, which is some millivolt value coming out of your Wheatstone bridge, to be from 0 to 3.3. Because that is going to be able to make us take the most amount of advantage of the ADC on the PCBs, or like the ADC on your TNC or on your Arduino. It's tuned to output, or it's tuned to like return a digital value for something between 0 and 3.3 volts. So, if for example, at 0 strain, right, or at 0 input, you're getting 1.8, right? It's just a base value. You can go up to 3.3, you can go down. For more illustrative purposes. You can go up to 3.3. Actually, no. I like 0. You can go up to 3.3 from 1.8, or you can go down to 0 from 1.8. That gives you sort of the same amount of range on both sides, going in the forwards or in the backwards direction, if you take that back to the sort of the torque on the axle analogy. And you'll get the same amount of granularity. And if you actually want to increase the range of the amount of like the strict newton meters on the member, you adjust it through here. If you want to adjust the granularity and in which direction you're going to see more or less of that max value, you adjust where your virtual ground sits. Yeah, you adjust where your virtual ground sits. So by changing this offset value, because this is just a voltage divider, it's pretty cool. Actually, yeah, I think it is. Yeah. By adjusting your offset, like the value of the two resistors on the string PCBs right now, or by turning the trimmer pot on some of the newer PCBs, you're going to adjust where your virtual ground sits. So if your virtual ground sits at, let's say, 3 volts, you're going to saturate at 3.3 super fast in one direction, but you're going to have so much more granularity in the other direction. You're going to be able to see the loads, or you're going to see the torques in a much more granular way, and you're going to have access to more of that range. Yeah, so which direction you're going to see more range. That's what this sort of circuit does. And then these are all just inputs and outputs and various other JSTs and stuff. So that's the PCB as I understand it for the most part. This was developed, I want to say, summer between the 2021 and the 2023 cars. It's pretty cool. It sits in the DAC box, so if you can sort of picture the DAC PCB, there's some like there's some DuPont jumpers that are like here and that are like here, and this PCB just sits right on top of those. So it's getting 3.3 and it's getting ground right from the DAC PCB, and then it's taking in that analog channel right in the middle, just right in there, so it's pretty cool. And then we fabricate wires to take us from the PCB all the way to the Wheatstone bridge that we make on the tubes, or wherever they end up being. So that is where we were at the end of last summer, for the most part. We were playing around with camber links, tie rods, steering columns. We were just starting to play around with the axles. We were trying to make this PCB work on the axle. So I only had like one half of this board populated, the other half I didn't have populated because we didn't really need it, because we weren't measuring torsion in the axle at 2 points or something like that. So I had it built up like this. I had a battery pack strapped to an axle. I had this strapped to the axle, and then the strain gauges were applied in this manner. It was the really cool, like this. I had strain gauge going like this and like this. And we built the Wheatstone bridge on there on both sides too. And what did we get with that? Oh, and we also had an ESP cam board. So the ESP cam board is a really cool little development board. It has an ESP32S2. It's really small. It's meant for like, you have like a camera attachment to it. And you use it for wireless monitoring or stuff like that. But it worked really well because it had, I think, one GPIO ADC pin exposed, and the rest were being used by the system. But it had one, which is all we needed, because all we needed it for was one. It was a board that was pretty much the exact same size as this. We just built the housing, and it worked a couple of times, but keep in mind that this was also all spinning on the axle, so it'd get flung around and covered in plastic, and it would get wet and this and that, so it was wasn't really all that great. And then this was actually around the time the accident happened.
Rest in peace.
Is when I switched over to a different idea of actually just making a standalone PCB. So I don't think I have Altium on this computer, but yeah, the newest revision of what I worked on and this was in like November or something, it was just one half of this board. So it's like just this half or something like that. And then an ESP32 built onto the board, like sitting over here, and it had an SD card just reflowed on there for memory storage. And yeah, it's essentially going to be the new wireless strain board. If you're interested in PCB design, definitely talk to me about this, because I've been trying to get it to work for a little while, but it's not really been working, so we can work on that together. And yeah, that board is going to sit on an axle. It's hopefully just going to be one board about the size of this one, plus a battery. And it's a really small LiPo, it's really nice. And it'll spin, and it'll gather data, and we're going to hijack a bit of Schmidt's web UI that he made for a UFO transducer, and just be able to access that and download it. It'll be really cool. Access all the data right off. And that'll be really cool. But for the rest of the strain gauges, we'll just probably just end up using this board. There's nothing wrong with it. But yeah, that's what I have for right now. This last thing is calibration. Yeah, like I alluded to a couple times. Can I draw it here? Yeah, so like I alluded to a couple times, you can either use strain, like use the gauge factor equation to get your strain, and then do something with your strain to convert it into whatever statics equation, use whatever statics equations you want to get into something that's useful. Or you can just straight up connect your amplifier board through this port to an oscilloscope and apply different loads to your member and actually see what voltage output it gives you. Plot that in Excel using the linear regression. Just get a thing, you get a y equals mx plus b. And you input your M and your B into the data viewer, and there you go, you got your force, and you got your torque, and it's really cool. We have a couple funny setups for that. For bending, for the most part, you just hold one end in like a vise or something, and then you progressively add more and more weight on the other side, and then you see what the voltage output is on the oscilloscope. For the tie rod and the camber link, who we were measuring axial through, there are two posts in hatch between the bays, and two really big I-beams that went all the way to the ceiling. And we put a tie rod in between and ratchet straps on either side. And we had a little force meter sitting in line in series with all of this. And we just kept ratcheting until we saw something on the oscilloscope. And then that's how we got our y equals mx plus b equation. It's a little sketchy, but it worked. And I have no doubt that we'll do that again for tie rods and camber links this year, because it worked really well in the end. It was pretty cool. And then for axles, take an axle out, put it in a vise, and then use either the small or the big, what's it called? The wrench you use for torquing down, no, torque wrench. Use a torque wrench to just get your input torque onto your member. The oscilloscope is going to look like you're going to have nothing, 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 all of something, 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 and then nothing, 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 also something. And these are when you're applying your loads. It should look more like this, go and then go. Like this. This is when you're actually applying the torque, and this is when your torque wrench clicks, and then all of a sudden you let it go because you get scared. And then this peak voltage is what you put in your equation, I don't know how to write it, or you put that into your Excel. And that is how you calibrate. You take that Excel sheet, I have examples on my other laptop, but yeah, you take that Excel sheet, get your y equals mx plus b equation, input that in the data viewer, and collect some data. And that's about that. Yeah. Any questions? Thank
You know a lot, Zach.
you. Yeah.
Really,
That's a lot to know.
Yeah.
No, I feel like I came for much.
I absorbed so much.
I
so much
learned a
knowledge.
lot.
I would listen to him lecture about.
Oh yeah,
I
you're
need my
a great
classes.
lecturer.
Thank
You
you.
should
And the notes are so nice. Oh my gosh.
Yeah.
Everything's prepared.
Can you post these in the chat?
Yeah, I'm going to clean them
Okay.
up. I'll post them.
Beautiful.
I'll put on the wiki page.
Ooh. We start linking this in the wiki.
Yes.
All the videos.
Wait, you can stop recording.
Oh, yeah.
Put that shit on the wiki.
Anybody have any questions?
Any questions before I stop recording? 3, 2, 1.